Hello and welcome to the day 3 of week 4 of this course. So, today we are going to deal with certain properties of irreducible representation, which we mentioned that they are most important type of representations, and particularly when we will deal with problems related to, say, valence theory or molecular orbital theory or spectroscopy. There this irreducible representations will be used a lot. Now before doing that, let's quickly recap what are the things that we learned in the last 3 or 4 classes. So we learned to make the representation, matrix representations of the symmetry operations, and thereby forming a set of matrices which define the matrix representation of a group. And we also learned that this representation may or may not be reducible. So, when we get a representation, one can try to reduce it by doing similarity transformation and making the matrices block factor, and ultimately reaching an irreducible limit. Now, then we also looked at a table called character table, which we tried to describe, and we saw that this character table deals with the characters of irreducible representations, and the number of irreducible representation for a given point group is fixed. We dealt with a point group C3V in the last class, and we tried to divide the character table in 4 parts, 1, 2, 3 and 4, and we described the different regions of those character tables, and the area 3 and 4, if you remember from the last class, we also showed that this area 3 and 4, they provide some linear or non-linear functions which can transform as one of the irreducible representation of that particular point group. Those particular functions will be extremely important when we go to the actual application part, which will come maybe in another week or so. Now, let's get into today's class, so where we will deal with a particular theorem. So, all the properties of a group representation and their characters, which are important when we deal with all these problems in valence theory or molecular orbital theory or spectroscopy, as I mentioned. Those properties can be derived from one particular theorem called the great orthogonality theorem. So, this basic theorem, it concerns the elements of the matrices which constitute the irreducible representation. So, this particular theorem, we will not prove this theorem, but we will just mention this theorem and then explain that, and we will try to utilize that theorem to achieve our goal, in a sense, like finding out the properties of irreducible representations. And this particular theorem will be extremely important, not only to deal with all the properties of molecule, but also using this theorem one can actually form the character table. Like when in the last class I showed you a character table of C3V, and I mentioned that these are the irreducible representations that are found that are possible for this particular point group. Now if you ask me, how can I get all this irreducible representation, or in other words, how can I form the character table? So this particular theorem will give you the ability to form the character table of any given point group. Okay, so what this theorem says, it says the great orthogonality theorem. So we will write it in short as GOT, great orthogonality theorem. Okay, so its mathematical form is given as uh, I will explain all these terms. So this is the mathematical representation of the great orthogonality theorem. So this is an extra bracket, we don't need this one. So let's first talk about this terms that are present here. So H, as we already know, is the order of the group. Okay. This L, I or Lj, they are the dimensions of the irreducible representation. So what is the dimension of any irreducible representation? So for any given irreducible representation, you have the matrix. Okay. So the order of that matrix is the dimension of the representation, or in other word, I can say it is the dimension of the it is the character of the identity operation for any given IR. Okay, any irreducible representation. Okay, and R is R stands for symmetry operations. So for any given symmetry operations, R will change, like R is E, R can be Cn, R can be Sn, all these things. And this gamma of R is any particular irreducible representation, and this Mn stands for a particular element of that particular representation. Which particular representation? Here it is ith representation, and this is the jth representation, right? So in the character table, we have seen that there are several different IR stands for irreducible representation. Now for any given IR, I have the matrices, and I can choose any element from that matrix. Fine. So if I choose one element from one particular matrix corresponding to one particular irreducible representation, and then I can have another one from another irreducible representation, and these are the Kronecker deltas relating I and j, that is two different IRs, M prime, that means two different elements, and also N prime, two different elements. So now what does this mathematical relation mean? So this means that in the set of matrices constituting any one irreducible representation, any set of corresponding matrix elements, one from each matrix behaves as the component of a vector in h dimensional space. Also, it says that all these vectors are mutually orthogonal, that is given by my delta functions. Okay, and moreover, such vectors are their lengths are normalized. I mean, they are actually rather their squares are normalized to h by Li. Okay, so this is the interpretation of this theorem in a nutshell. Okay, so what it says, if I repeat again, is that if I take one particular element from the matrices corresponding to the one particular irreducible representation, and we keep picking the same type of element from each of the matrices in the set which forms the representation of the group, then this forms a vector. This behaves like a vector, and overall it behaves like a vector in an h dimensional space, because we have h number of elements in the group, right. So h number of elements in the group, therefore h number of matrices in the group, and we are picking one element from each matrices and constituting a vector. So there will be h dimensional vectors, and these vectors are all mutually orthogonal. And not only that, the square of the length of these vectors are equal to h by li. Now it will be more clear if we split this big equation in comparatively 3 shorter equations. So let's first we can write in this way. By the way, one thing I missed out here, what is the star? So star corresponds to the complex conjugate. So this representation can have complex quantities. So therefore, one of the matrix element, we should take the conjugate of that matrix element. Now we will remember that we always have to put this conjugate, but for convenience we are removing this star here, but we will keep that in mind. So so okay, I can skip this part. So I can say directly that this will be 0 if I not equals to j. So this can be verified from here. So instead of choosing different elements, we are choosing the same particular element from each matrix. Now we are choosing from 2 different irreducible representations correspond to I and j. So ith and jth irreducible representation. So this product and their sum over all the symmetry elements, symmetry operations will give me 0 until and unless I is equal to j. What does this mean? That is, if the elements do not belong to the same irreducible representation, then they will be orthogonal. Okay. So what we can say if I look at any character table. So I have 2 different irreducible representation, right. So now if I try to do the same if I want to multiply 2 different irreducible representations, then the character of the irreducible representation, then they will give me 0. But if I do it with with itself, like choose one particular irreducible representation and multiply with itself, then that will not be 0. Okay. And if I choose the same irreducible representation, but if I do not choose the same element, then what will happen? So if I choose same irreducible representation, but say So okay, then this will be 0 until unless m equals to m prime and n equals to n prime. If this doesn't hold, then this part will be 0. Okay, and thirdly, gamma I r this will give me the value of h by Li. Alright, so these three are actually the simplified version of this mathematical framework of this great orthogonality theorem. And we can see here that if I take the irreducible representation and if I choose the same irreducible representation and the same element of the matrix, and if we multiply them and then ultimately sum over all the symmetry operations, then I get the essentially I get the square of the length of the vector. If I think that taking all these elements one each from each matrices from the set of matrices which gives me the representation of the group, then they behave like a vector. So essentially it is the length of this part is the square of the length of the vector and that is equals to h by Li, where Li is the dimension of the present representation and h is the order of the group. Okay, so this three equations will be very much useful for us. Now we will deal with certain rules that results from this great orthogonality theorem. So the first rule, so rule 1, what it says? It says that the sum of the square of the dimensions of the irreducible representation of a group is equal to the order of the group. Okay, so mathematically, if I want to say that, that is equals to this. So Li represents the dimensions. So it says the sum of square of the dimensions of all the irreducible representation of the group is equal to the order of the group. Okay, so one can prove this this particular rule, but that is pretty tedious, and we will not try to prove this one. But one thing that we can figure out from this particular expression is this, that Li, if I have to find out the Li from the character table of any particular point group, and Li means the dimension of ith irreducible representation. So how do I know that? So if we look at the character of the identity operation, okay, because identity operation will have all whatever the order of the matrix, it will have 1 as its diagonal elements, right? So therefore the sum over all the diagonal elements will tell me what is the order of the matrix. That means what is the dimension of this representation. So for example, like if I have a 2-dimensional representation, so identity matrix will give me this one, right? So this representation is a 2-dimensional representation. That means L equals to 2 here. So now if I look at the character under the identity operation, so what will be the character here? So chi of E here is equals to 2 because 1 plus 1 equals to 2. So therefore, if we want to figure out what is the dimension of any given irreducible representation, then all I should do is to look at the character of the identity operation, okay, for that representation. So since this is the relation between the dimension of the representation and the character of the identity operation for that particular representation, then I can rewrite this one like this, chi I of identity square equals to the order of the group. Okay, this is an useful relation. Okay, so this comes from this rule 1. Now we can have another 4 different rules. So let's look at rule 2. So rule 2 says that the summation of the square of the characters for any given irreducible representation is equal to h, the order of the group. So mathematically what we can say is this character of any given irreducible representation, say for example ith representation for any operation is given by chi I of r, and if I take the square of that and sum it over all the symmetry operations, then that will be equals to the order of the group. Okay, so we can easily prove this one. How? We can take from this expression itself, and we can write sum over r. If I take any particular ith representation for any given operation, and okay, so this should be equals to h by Li delta m prime, because I have chosen the same irreducible representation, that is ith representation. So delta ij in the original form of great orthogonality theorem gives me unity, and we are left with 2 delta m prime. Okay, so now excuse me. So this one, that is chi of r, this equals to okay, let me start from the other round, so that will be helpful for you. So if I sum it over m and m prime separately on both the side, then let's see what happens. So if I say sum it over m and m prime on this side as well as on okay, then let's figure out what do we get. So the order of summation is immaterial. Okay, so what we can do, we can rearrange this one, and we can have sum over m gamma I r m m, and sum over m prime gamma I of r m prime m prime. Fine. So what does this give me? Because gamma I of r m m means the diagonal element, and I am summing it over m, that means it will give me the trace of the matrix, that is character of the representation. So this is nothing but the character of ith of the symmetry operation R for the ith irreducible representation, correct? And same thing is here. So summing over m prime, and I have the elements as the diagonal elements m prime m prime. So this will also give me the character of the operation R for the ith representation, ith irreducible representation. So this is nothing but the square of this chi of R, right? So this is equals to sum over R chi I of R square, correct? Now let's look at this part. So if I take out this h by Li outside the summation, so this summation, this one, this will give me h by Li and then 2 summation over m and m prime of delta m m prime. So that is going to ultimately give me Li, because this m runs from 1 to Li, correct? Because that's Li is the dimension. So ultimately I will get Li, correct? So this is going to give me h. So thereby this part is equals to h, and that's what this rule says, correct? So this is the way you can prove it, fine. So what does it mean? If you quickly look at the character table for C3V, okay, which is on your screen, and take any representation. So you have, let's choose A1. So if I take the squares, so what will happen? So of course here one thing you should notice that all the symmetry operations belonging to the a particular class is clubbed together, and their characters are same, that we have already proved earlier. So when you want to sum over all the R's, so you have to keep in mind that say for example C3 has 2 different symmetry operations, and sigma v in that class we have 3 different symmetry operations. So ultimately if I look at the irreducible representation A1, what I have, if I want to sum over all the symmetry operations, sum over all the symmetry operations, and we get 1 plus 2 into 1 plus 3 into 1 equals to 6, and order of the group is also 6. We choose another one. Let's choose the representation E. So here E will give me 2 square minus 2 into 1 plus 3 into 0. Okay. So what is the ultimate value here? So we get the again the order of the group. Okay. So that is the rule 2. Okay. So now let's go to rule 3. So rule 3 says the vectors whose component belong to 2 different irreducible representations are orthogonal. Okay. So what does it say? It says if I have if I not equals to j. Okay. So these are the characters for a given particular irreducible representation. Now if we have the characters for any given symmetry operation R, if we multiply that with another the same character for another irreducible representation J and then sum it over all the symmetry operations, I will get 0, meaning this and this are orthogonal. Okay. So, how do I prove that? We can choose here this particular part and we can slightly modify that. So, if I look at the first equation, what we can write, okay. So, this will be, here I am using only m equals to n, okay. Rest of the things are same. So, this will what it should give me? It should give me 0, right. So, this one, if I rewrite, this is equal to, if you think carefully, if I sum it over m, then I get chi I of r, correct. So, if I write that, chi over m gamma I r m m. So, this is my this part chi I of r, and if I again sum it over m for j, I get the character for jth irreducible representation, right. So, this part I have already seen. So, this is since we are summing over the same m. So, instead of writing this, I can club it all together, right. Now, this I have already got as 0, correct. This is exactly written here. So, this part is also 0. Only in case I equals to j, this will be non-zero. Okay. So, in that case, that will give me the value of the square of the length of the vectors, that is the irreducible representations here. So, that is rule 3, and the rule 4 says that in a given representation, be it reducible or irreducible, the characters belonging to the matrices which form a class are identical, which we have already seen in one of the previous classes, that we saw it in a different way, that the conjugate matrices have identical characters. Now, we think about it, that is in a class all the elements are conjugate to themselves. If they are conjugate, then their corresponding matrix representations, does not matter whether it is reducible or irreducible, they will also be conjugate to each other. So, that means they are related through a similarity transformation. Okay. So, therefore, their characters will be identical, which we have already proven. Okay. And then, so this was rule 3, and the characters for all the symmetry operations belonging to a particular symmetry operations belonging to a particular class are identical. So, with this we will stop here, and we will continue with the other rules that are corollaries from the great orthogonality theorem in the next class. Thank you.